We have a box that is being dragged to the right with a force, and it also has a drag force acting in the opposite direction. K is a positive constant, so let's go ahead and draw the forces acting on the box. We have a normal force, we have the weight, we have the applied pulling force that's constant, and we have this drag force kV like that. Now for part B it says write down but do not determine the speed v of the box, just the differential equation. So for part B, what we will write is that mg minus kv, thinking ahead here, we have the applied force minus kv equals m times a, and we realize this is the differential equation we're going to need to solve using Newton's second law. So Fa minus kv equals m dv dt. So with that in mind, we can actually go ahead and determine the terminal velocity of the box. So to be clear, for C, at V terminal, A equals 0 because the force is balanced. So we can say Fa minus KV terminal equals m times 0, which is 0. So the terminal speed is just going to be the applied force divided by that drag coefficient or drag constant. Now for part D we do want to solve the differential equation, so we're going to go ahead and do that now. So we're going to say that Fa minus kV equals m dv dt. I'm going to go ahead and do a little bit of math here to isolate the t stuff on one side and the v stuff on the other. So what we will say is that dv over Fa minus kv equals dt divided by m. And now we're going to do a u substitution. U is going to equal Fa minus kV. And again, I know that you've learned different ways of doing u substitution, so my way is not necessarily the wisest or the best. So negative du over k equals dv, and those are the two things that I can substitute. So I can say negative du over k times 1 over u, and we're going to take the antiderivative of that, is going to equal the antiderivative of dt over m. We're going to multiply both sides by k. So that means we're going to get du over u equals negative, and I need to have my integral signs, k over m dt. Continuing, I'm going to get the natural log of u equals negative k over mt. Oh, and this is going to be natural log of u plus c to get the integration constant. Now, one thing is that it's initially at rest, so one thing we want to note is that v of 0 equals 0. Now I'm going to substitute my u expression back, so I'm going to say that the natural log of Fa minus k times 0 plus c equals negative k over m times 0. And so what that tells me is that c is the natural log of Fa, actually the negative natural log of Fa. Okay. Continuing with my now solved integration constant in my now solved differential equation, I can say ln of Fa minus kv, and now combining my integration constant, that's over fa, equals negative kt over m. I'm going to exponentiate both sides, and when I do that and simplify, what I'll get is that v of t equals fa over k, 1 minus e to the negative kt over m. So this will be our answer right there. Let me just be careful with that. So again, that's going to be fa over k, 1 minus e to the negative kt over m. That's our answer. All right, now it says on the axes below, graph a sketch of speed versus the function versus t. So we will reach this asymptote right here. Just to be clear. And that asymptote is going to be the terminal speed, fa over k. All right, so that is the 2013 mechanics question.